Now what we're going to do is take a look at a pretty classic example of an application of some graphs. Again, since waves are so common, compression waves, vibration, sound waves, it usually turns out that sines and cosine graphs are much more applicable to our real world, and so that's why we kind of pay attention to them a little bit more. And what we're going to be talking about here, this classic example in 4.5, is an example of what we call simple harmonic motion. And really what it is, in its most basic sense, it's basically when we have an object that's allowed to swing back and forth between its equilibrium. So I've got a spring, I've got a little mass on that, and so when I pull this string or when I push it up, what it's going to do is cause the spring to snap back into its normal equilibrium. And so this weight will basically slide back and forth. Of course, we could also move around in a circle, right, of some radius r. We're going to keep going right back and forth, and the equilibrium would basically be where we have started, right, and then we'll move away from it and come back around. So basically, whether we're moving around in a circle or in a spring mass system, or we even have pendulums, right? A pendulum, basically like in a clock, basically just swings back and forth. So it has some distance away from its equilibrium and some distance away from the equilibrium. So it just keeps bouncing back and forth. So lots of ways to just describe a simple harmonic motion situation. It is usually some sort of a circle, all right, is what we usually have in application. So what does this displacement look like? Well, if we assume that there is no shifting left or right, all right, and so that's one assumption we do. So we'll always make the equilibrium 0. If the equilibrium is never 0, we can always just take our graph and shift it up or shift it down and put it right along, right, the XY axis, if you would. So that's one of our first things. So no matter what, when we're in simple harmonic motion, we'll just assume that the equilibrium will be equal to 0, and then we're also going to assume that there's no phase shifts going on. Okay, and again, that's pretty easy because if I have a situation that's in simple harmonic motion, I can just simply move my x and y axis up and down or left and right so that I match a cosine graph starting at a high point or a sine graph starting at a low point. So really all we need to worry about in simple harmonic motion is what we call the A and the B. And classically what's going to happen if we're a sine curve, if we're starting at equilibrium, at some point, the sine curve is going to reach its maximum, right? At another point, it's going to come back to its equilibrium. It's going to reach a low point and then come back. So that this would be like if I took this mass and forced it up, right, to a high point and then let it go. It's basically going to be bouncing back and forth, back and forth, back and forth, right? And so we're going to start at 0, hit a high point, right, come back to a low point, come back, and we're just going to keep going on and on and on forever. Okay, so we basically have a sine of bx to match that. Okay, or right, potentially we start at that high point. Let me put it in red. So if I start up there, we start at the high point, and then we come back through the equilibrium, come to a low point, back to equilibrium, right, and back at a high point. So what I have in red is some A cosine, right, of bx. And of course, we can make A negative so that we're actually starting down here, right? So I pulled the string down here, and we started here and did that action, so A would be negative. And we've seen all that before, way back in 4.1 and 4.2. And so basically what we have to mathematically model simple harmonic motion is we essentially have a basic cosine curve or a basic sine curve. And that's the next part. So our formulas for this, we're actually going to continue to call A, right? A will still be amplitude, but we're going to switch out. B is now that omega. And so our displacement, that's what S represents. So our displacement from equilibrium, right, in a certain amount of time t, right, is going to be given by this formula. Where A is the amplitude, how far above and below we are of that equilibrium, and this omega is called the angular frequency, and it's measured in radians per second. But we've actually seen that before, right? When we're measured in radians per second, earlier we called this, I think it was in 3.4, we called this angular velocity. All right, so that omega is basically how fast, if we were talking about a wheel, right, how fast that wheel is spinning in radians per second. And so that's basically what that omega is there. Okay, as we've seen in the past, our new period for this thing is going to be my old period divided by that omega. So that doesn't change anything. That kind of mirrors what we did before. And this will be measured in time, like seconds, minutes, or whatever we're using. And then the thing that's new here is this thing called frequency. Frequency is basically the reciprocal of the period. So if the period is 2 pi over omega, then the frequency is is omega over 2 pi. And the frequency basically is measured in oscillations per unit time. So you've kind of heard me refer to that in a normal 2 pi sequence, how many full waves do we have? If we have 4 full waves, then my frequency is 4. If I have 2 full waves, my frequency is 2. All right, and again, we get that from the period. So if my period changes from 0 to pi, that means over the normal period from 0 to 2 pi, our frequency would now be 2. All right, and so that's what that would basically mean. We go through 2 cycles per second. And so that's probably new to us in this thing. So we're basically back to 4.1, where we're graphing cosines and sine curves, we're impacting amplitude, and we also have B, which is tied together with our angular velocity from way back in the day. Period's the same, frequency is the reciprocal of that period, and so we get the new stuff. So armed with our formulas and what the S and the T and the A and the omega are, let's go do some word problems.